And we're back. We're doing more CLEP calculus practice exams that I grabbed off the internet at these addresses, link in the description. And we are still in that first one in the second section of the exam where calculators are allowed, at least when making use of the calculator is helpful. So starting right back off at number 46, we have some function that is differentiable, which just means it's a normal function with no crazy interruptions. And for that original function, at an x value of 1, y is 20. And at an x value of 4, y is negative 4. So it's asking, which of the following statements must be true? Okay, so we have to look at these one by one. Roman numeral 1 is suggesting that the first derivative of that function is less than 0. What would that mean? We're talking about where the original function has a downward slope, a negative slope, for all values of x in that interval between 1 and 4. So at 1, at x equals 1, we're starting up here at 20, and at x equals 4, 3 steps of x further on, the y value is way down at negative 4. So to get from here to here, is the graph always headed in a downward direction? And yeah, it might be. We think it might be, but it could go down past and back up. It could go up and then back down again. It doesn't necessarily have to go straight from here to here. And also that if it goes straight there, yes, that is a downward slope, and the derivative is negative, less than 0. But if it does any kind of loopy thing, if it comes up and back down, or goes down and back up, then there is some portion of that with a positive slope. So we can't say Roman numeral 1 for sure. It doesn't have to be true. It might be true, might not be. We don't have enough information to say that it absolutely has to be true. So Roman numeral 2 suggests there exists a certain number c where c is between 1 and 4, such that the function at that value is 0. So basically we're saying there's some value of x somewhere between 1 and 4 at the x value where the y value is 0. So basically we're saying between x at 1, where y is 20, and x equals 4, where y is negative 4, that the function, that the y equals 0. So we're just saying that to get from 20 to negative 4, that we have to cross the x-axis at some point, at least once. And that's obviously true. And there's no way that you could argue for that to not be true. So that definitely has to be true. We know that's true. And then number 3 suggests there exists a number c between 1 and 4. So again, some x value where the derivative at that x, so somewhere along that stretch between 120 and 4 negative 4, that the slope equals negative 8. So what's special about negative 8? Well, if we think about the 2 points that were given, 120 and 4, negative 4, what is the actual slope between there? So the change in x minus the change in y. Doing that correctly? Change in y? No. Let's do it this way. Let's do the second point minus the first point over the second point minus the first. Change in y over change in x. Second point minus first point, second point minus the first point. And what that is, we get negative 24 over 3 equals negative 8. So if we just drew a straight line between those 2 points, it does have a slope of negative 8. But remember, back in Roman numeral 1, we said we don't know for sure that it just goes in a straight line. It could curve up and back down. It could curve down and back up. But if you think about it, and this is actually, I believe this is called the mean value theorem. If you think about it, that if you are drawing, let me draw it out. If you have your point up there and your point down there, and there's your straight line slope, and maybe it's going down and back up, maybe it's going up and back down, but there's really no arrangement where some slope is going to be tangent to this. If it's going up and back down, you're going to have parallel slope somewhere around there. If it's going down and back up, you're going to have some parallel slope around there. Just like crossing the x-axis is unavoidable, it's unavoidable at some point, because if you're going down, you have to go back up. If you're going up, you have to go back down. At some point, you have to hit a slope that is equal to the straight line slope. And there's probably some fancy mathematical proof for that, but we can just look at the picture and use our heads and say, yeah, that must be true. And like I said, I believe that's called the mean value theorem properly. But you just know it intuitively. So number 3 also must be true. And where 2 and 3 are the true ones, that is selection D. And that is the answer to that one. Didn't even get to use the calculator. All right, moving on. Number 47. So we have some g where the derivative of g is this messy thing, the tangent of 2 over 1 plus x squared. And so g is some function with that first derivative. And in the original function g, where x is 1, y is 5. And now we're talking about some function f, where f is the natural log of that original function g. So now what is the value of the derivative of that at x equals 1? So we can see here there's going to be some kind of chain rule involved. So remember, for the chain rule, it tells us that for a composite function f of g of x, to find the derivative of that, it is the derivative of f of the with the original g part inside of it, and then times the derivative of that inside part, the g. So we already know that g at 1 equals 5, and we know that the derivative of g is this thing, So the derivative of g at 1 is going to be the tangent of 2 over 1 plus, fill in the 1 for x, so it is 1 squared, and that's a plus. 1 plus 1 squared is just 1 plus 1 is just 2. 2 over 2 is just 1. So the tangent of 1. And then the f is that natural log, some x, and the derivative of the f. And here's one you just have to know. One of those fancy derivatives that it's good to memorize. The derivative of the natural log is just 1 over x. By the way, as an aside, what is the natural log? Do you know what the natural log is? Well, if you think about a normal logarithm for, if we say the log of a equals b, base 10 log, the normal base 10, what that is saying is for some value of 10 to the power of b, it's equal to a. So for instance, the log of 100 equals 2, because 10 squared equals 100. So the natural log is the same thing as that, but with the base e, that very special number e that does a lot of fancy things, such as e to the x is its own derivative. There's a lot of special things around that number e. And this is another one of those special things where the logarithm base e, known as the natural log, when you take the derivative of that, it just becomes the very simple 1 over x. And you just need to remember that. So now we need to do that chain rule. So the derivative of f, which is 1 over, and then you have to fill in for that x, you have to fill in the g of x, and we want to know what it's equal to at 1. So we're going to fill in the g at 1, and that's going to be 5. And then we multiply that by the derivative of g at 1, because that's what we're interested in. And so that's 1/5 times the tangent of 1. And then here's where we're glad we have the calculator, because we can say the tangent of 1 divided by 5 is 0.3114. And we look over here, and 0.311 is a option at A, and A is indeed the answer. So aren't we glad that we have the calculator on that one? A trig value at something that would not be pleasant without the calculator. Okay, moving on. Number 48. R is a differentiable function. Again, differentiable just meaning you can take the derivative and it goes smoothly. There's nothing crazy happening. There's no sections where it does different things or has a discontinuity or changes to a completely different function halfway down. That is positive and increasing. So it is, we know it is above the x-axis, and we know it's going up. We know the slope is positive for the entire thing. We know that the first derivative is positive for the entire thing. So the rate of increase of r to the third power is equal to 12 times the rate of increase of r on its own at what x value? Okay. So, what are we asking? When we say rate of increase, again, we're talking the slope. Say, you know, what is the slope? So it's saying that the derivative of r cubed equals 12 times the derivative of r somewhere. And where is that somewhere? So let's see. Okay, I think about this a little bit. So we have some r of t, and the derivative of that would be the notation r prime of t. And then if you cube that, r of t cubed, it's not the t being cubed, but the whole thing being cubed. And how do we find what some kind of equation for the derivative of that, the derivative of the slope when you take the whole equation and cube it? And if we think about that a little bit, this is a chain rule again, because you're taking some function, it's a composite function, you're taking some function and doing another operation to it. So your f of g of x, the derivative of that, f prime g of x times g prime of x, where g of x is your rt, and that f is the cube, right? So your f is x cubed, and the derivative of f, simple power rule, bring the 3 down, subtract 1, is going to be 3x squared. So to fill that back in, you have the 3, and the original g, remember, is the r of t multiplied by the derivative of that. So it is r prime t. And we're saying that, remember, we're saying that the derivative of that is somewhere equal to 12 times the derivative of the original. So we're going to set that equal to 12 times the derivative of the original. We don't even have a proper equation. We don't even know what the equation is. We're just dealing with the theoretical equation and derivative of the equation. So boy, what can we do with that now? Let's see. And if we notice, there are actually some common factors on both sides. So if we actually divide both sides by 3 and the derivative of r, now that goes away, that goes away, that goes away, and 12 divided by 3 is 4. So we're left with r of t squared equals 4. And then just square root on both sides, r of t equals 2. So somewhere that t equals 2, or where r of t equals 2, that's where those two things are equal, where r of t equals 2, b. So yeah, it takes a little bit of of thinking there, where the same math still applies. You're just juggling this theoretical R of t without even needing to do anything about it. We can still do the the composite function with the f of the g, and not even knowing what the g is. We know what the f is. The f is the x cubed, but we don't even know what the g is, but we don't have to because it actually goes away. But you can, it's just to show that you can still play around with things even without really knowing what it is. Even if it's just a theoretical object, you can still go through the same type of operations you would ordinarily do, and they arrange it so that you do come to a real answer on the test. The problems are specifically designed so that you arrive at some real answer. All right, number 49. The function f shown in the figure above, at which of the following points could the derivative be equal to the average rate of change? So the average rate of change, we're talking about the slope. Again, if you have a point here and a point here, well, what is the average rate of change, even if it's going up and coming back down again? If you're averaging the rate of change, that is just the straight line slope between those 2 points. So where is the slope of f equal to the overall straight line slope between 2 and negative 4? So just think about, I'm just going to draw it freehand here. That's going to be about there. That's the average rate of change. That's the straight line slope between there and there. And this is kind of a mean value theorem again, where we know that regardless of what the graph is doing in between these 2 points, at least in one place, it has to have a slope that matches this. And you'll note on here, we can pick out somewhere along here and somewhere along there. There's going to be a slope. Just eyeballing it, you can say that the slope is going to be parallel to that, about here and about here. And by inspection, you can see pretty much it looks like it's going to be B. Because at A, the slope is up here. At C looks like it's a maximum. The slope is 0. D is going that way. E looks like it's a minimum. The slope is about 0. So pretty intuitive, pretty just eyeball it really quickly, and we can say that it is B, and that is indeed the answer. Okay. Moving along. Wow, look at this. So we have, inside we have e to the power of t, but then we are finding the definite integral of that in the bounds between 0 and x squared. And then we want the derivative of that. So wow, isn't that a big mess? So let's just take that one step at a time. Copy it back down here, d over dx. Definite integral from z to x, or 0 to x squared, e to the t dt. So first of all, remember that e to the x dx is itself the derivative of e to the x equals e to the x. So even though we're using a t here instead of an x, the same rule applies. E to the t in terms of t is its own derivative, it's its own integral. So if we were to do a definite integral for that, same way we would ever do it. So we're going to take the upper bound plug it in for the variable e to the x squared, and then we're going to subtract, filling in the lower bound for the variable e to the 0 power. And we also know anything to the 0 power equals 1, so we can just do that right away. E to the power of x squared minus 1. And then what is the derivative of that? And so, now that mess went away, and we're left with this mess instead, but it's less of a mess, and that's something that we can manage. And we're going to chain rule this because we have a x squared inside of another function. So if we think of a chain rule where f of g to the x, and the derivative of that again is f prime, the derivative of x with the g of x inside, times the derivative of g of x, in this case where f is e to, I won't use x just to avoid a little bit of confusion. I'm going to call it n instead. So the original f function is e to the n minus 1, and the original g function is that x squared. And so the derivative of f, we know again e to the n is always going to be itself, and a negative 1, there's no variable there, so it just goes away. The variable, you could say n to the 0 power, 0 comes down, multiplies by negative 1, makes it go away. And then the derivative of the g, again, simple power rule, 2 comes down, subtracts 1, that's 2x. So then we fill in on the power rule. So the derivative of f, we have e to the n, and we're going to fill in our original g back into there. So it's e to the x squared times the derivative of the g, 2x. And if we look at our options here, let's actually just say that the 2x goes in front. And that is, in fact, one of our options, 2 times x times e to the power of x squared. And that is indeed our answer there. And didn't get to use a calculator on that one either. A little disappointing. It's another tricky chain rule thing where we had to sort that bit out first, and then do a bit of chain rule thing. So it gets a little tricky. You just have to take it break it into the pieces, take it one step at a time, and you should get there. Okay, that's it for this time. See you in the next video.